Hi, I'm Terri Pigott. So we are going to talk conceptually today about individual participant meta-analysis. So I want to give you sort of an introduction to the topic and its rationale, why it's useful, a conceptual discussion of some of the simpler models that are used, some examples, and then talk a little bit about computing options. So, okay. In standard aggregated meta-analysis, we use data from our studies to compute measures of a study's effect. You know, those effect sizes are computed again from aggregated study data, aggregated study level data. So for example, we might compute a standardized mean difference from the information we have at the level of the study. But we also run into a couple of problems in aggregated and standard aggregated data meta-analysis. For example, we have missing information a lot of times in a study, published study or unpublished study, to compute an effect size or to code potentially important moderator variables. We also might have low statistical power for many reasons for computing moderator effects. And then we also have this potential for ecological bias, which I'm going to talk about each of these three separately now. So the question is, too, what if we had access to data from the individual level? What if we had the original data from the studies itself? So individual participant data meta-analysis, or in medicine, individual patient data meta-analysis, but we've changed patient to participant for the social sciences, refers to the situation where we have access to at least some of the original individual level data from the primary studies. While we could just go ahead and take that primary data and aggregate it up to the level of the study and then pretend like we have just a bunch of studies, there are some advantages to using the individual level data. So for example, we always have missing data. This is just that's just the situation we have to live with when we're doing a systematic review. And it's well documented in the medical literature, and we're beginning to see some work in social sciences, that reporting biases exist. Not all the information we need is reported in a study, in a primary study. We also have, at least in the social sciences, the inclusion of more complex quasi-experimental designs. Regression discontinuity designs, IVE designs, all these kinds of quasi-experimental designs that also use complex models to analyze the data. And they tend sometimes not to give us the kind of information we need to calculate an effect size. And I don't know anyone, except, of course, David Wilson, who's somewhere on campus right now, talking about effect sizes, I think, who doesn't have trouble finding an effect size. So having the individual level data would allow us to maybe calculate an effect size that could be comparable across studies. And also gives us maybe some of the predictors that we would wish we had when we're coding an individual study. We began thinking about IPD meta-analysis, we being some of my colleagues and I, when we were trying to look at how to combine regression equations across studies. So we thought, God, if we just had the data, then we could estimate the same model within each study, and that might be one way to get around that issue. So that's one of the motivators for this. Also power, IPD and power. One of the most interesting findings, usually from a systematic review, one of the reasons why we're doing systematic review, is because we want to understand how treatment effects vary across studies. But in many systematic reviews, we can only conduct limited moderator analyses. Sometimes this is because we don't have enough studies, and sometimes it's because we don't have the information we need. So there's a potential that if we had the individual level data, we might be able to do some of these moderator analyses more easily. There has been some empirical work on the power of IPD versus aggregated data meta-analysis. Lambert, 2002, did a simulation study that found that IPD was more powerful, it's fine, than aggregated data meta-analysis. But in that simulation study, it was a simulation study that looked at when we had all of the individual data available to us from all of the studies and not just a few. So, and then finally, pardon me? Oh. Finally, one issue here is what we always face when we're looking at aggregated data and aggregated study results is ecological bias. Lots of work in medicine, Jesse Berlin, Chris Schmidt, but bunches of people have looked at this issue of ecological bias and especially interpretation of aggregated data meta-analyses, moderator effects. So we always have to remind ourselves that when we're looking at moderator effects and meta-analysis, we're looking at how study level characteristics relate to study level outcomes. So we can't, for example, if we find that studies with a higher percentage of women in the sample seem to have larger treatment effects, we can't automatically assume that the treatment is better for women. So this idea that always our moderator analyses are observational, not causal. But if we had the individual level data for at least some of the studies, we could begin to answer those kinds of questions about how does the treatment effect relate to individual level characteristics as opposed to study level ones. Okay. Now, since we're at Campbell, we're going to talk about what happens in the social and behavioral sciences. Although I assume, I always assume that the grass is always greener on the other side, but this is as hard in medicine as it is in the social sciences. But we even have a little bit of a bigger problem in the fact that we have no history, really, at least in the US, of sharing data. I mean, there is no, I can't think of a single case where someone said, oh yeah, sure, you can have my data. So there are very few depositories of this kind of data, at least in the US, that could be used for IPD. We do have the National Science Foundation and the National Institutes of Health have begun to require some data sharing plans. I don't know how long this is going to take for us to actually have access to some of these. And then we also have access to large-scale nationally representative sort of survey observational data sets conducted by the National Center for Educational Statistics and other places like that. And data repositories such as the Inter-University Consortium for Political and Social Research, which is at the University of Michigan. And I know that they do have some quasi-experimental data that they've that they archive there. But we are, I think, a long way away from actually having some systematic way of finding, even searching for, and actually obtaining access to studies on treatment effects at the level of the individual. Okay. The only one that I know of right now in the social sciences is a paper by Goldstein in 2000, who looked at class size effects and used a combination of study level and aggregate study level and individual level data to look at the impact of small class sizes. Those of you who know education, this is the Tennessee STAR study, which was a large randomized trial in Tennessee that randomly assigned kids or randomly assigned classrooms to small, regular size and regular with an aid. And doing that, in that particular analysis, Goldstein did find actually larger class size effects by using this method than just looking at the results from the RCT by itself.
Is that Harvey Goldstein, by the way?
Of course it is.
I thought I wonder what he's doing in Tennessee. I suppose he gets around.
Well, he does, and I don't know. I also want that data is notoriously difficult to get, so I don't know what Harvey did to get it. That Tennessee STAR data for a long time was sort of no one could get their hands on it. So so anyway, but I think that's where we're going to be. I think in the social and behavioral sciences, we're going to be in the case where we're going to have a combination of study level and individual level data if we're lucky. So I think that we're not. There's a lot of research on what happens when you have all of the individual participant data. But what I'm going to talk to you about here is just looking in general at some models where we have both, because I don't see us having the full thing. Yeah. Okay. So there are sort of two methods people use to incorporate the individual level data. A two-stage method, and one way to do that, and one sort of method people use in two-stage method is it's a standard meta-analysis. You just happen to have the IPD. We aggregate it up to the level of the study, synthesize using traditional methods, but we're not really taking advantage of the fact that we have the individual level data. And then what Riley, this is all actually from Riley's paper in 2008, calls the one-stage method, which is we have the aggregated data from the studies, and then we estimate models that use both the aggregated data and the individual participant data. Okay. So the one way to think about it is we're actually doing sort of a multi-level model, right? We have data, at level 1, we have data from the individuals, and at level 2, we're looking at study level models. So sort of I'm going to give you some sense of what these models look like. So to introduce these models, when we're combining aggregate and IPD, let's imagine that we only have IPD data. So for every study, we have an outcome that, for every study I, we have an outcome, Yij, and an indicator variable that tells us whether the person is in the treatment group or the control group, or whatever group, female, male, whatever it might be. Okay. So what we basically have then is a typical two-level model where we have the individual level model. We have a fixed effect for every study. This is our treatment effect. This is our indicator variable for group. This is our level 1 model for the individual observation, and then our level 2 models at the study level. So typical multi-level, two-level model that we use if we just have the individual level data. Okay? And then we're going to get our average treatment effect here. Okay. But now imagine we have both. We have aggregated data and individual level data. So, our IPD studies are going to give us some information about, give us information for level 1, and then our aggregated data are going to give us information about level 2. So our aggregated data is only going to contribute up to our estimated average treatment effect in that case. Our first problem in this situation is that we sort of have two different outcomes. At the individual level, we have our individual estimates, our measure of treatment effect. But at level 2, for our studies, we have some kind of effect size. So we have to do something about that so we have the same, we can compare across studies. So what we do is, and this is, I think, one of the features of these kinds of models, there's a lot of modeling tricks that go on here, a lot of clever kind of modeling tricks that you use in order to make this work. Okay. So we start by standardizing our, if we're thinking about, in this case, the context that I've been talking about are treatment effects. So and our interest is in a standardized mean difference. We can, if that's our outcome and we're looking at some kind of treatment effect or some kind of group difference effect across studies, we could standardize our outcome. So this is our individual outcome at our individual study level information. So our outcome for individual J and study I, and we can standardize it on the treatment effect. And so subtract the treatment effect, the mean treatment, a mean, and then divide by the standard deviation of the outcome.
Is that a grand mean? That's for
the grand mean. The grand mean in that study, yeah.
In that study, so it's
for the treatment effect, yeah.
So it's a TJ, really, isn't it?
Oh yeah, sorry, yes, TJ, sorry. So this is, yeah, standard, not the grand mean across all the IPDs, but the grand mean in that study. I'm sorry, you're absolutely right. So we're going to use for each individual's outcome, we're going to subtract their study treatment mean and divide by the standard deviation in that study, the pooled standard deviation in that study. Okay, so we're going to have this standardized variable within that study to be our outcome at the individual level. Okay, so what that does then is, allow us then to estimate a treatment effect that's going to be equal to the standardized mean difference at level 2. Okay, so we're going to need a couple other things for our study. For this model, we're going to need an indicator variable. just to say whether the study is aggregate or IPD. So again, our outcomes for our IPD studies are these standardized on the basis of the treatment effect, and that's the treatment mean in that study. And then our outcomes for our aggregate data studies are going to just be our standardized mean difference, which I'll use D. So it'll look this in the simplest model. It looks something like this. Okay. So for an IPD study, we have our sort of standardized outcome. We have an indicator variable, so this is only going to come up when we have IPD studies. This is our fixed treatment effect. Then we have, for an individual within a study that has individual level data, we have an indicator for whether that person is in the treatment or control group. And then at level 2 again, which stays the same, we are going to estimate our average treatment effect. So that's using that kind of standardization at level 1 lets us estimate, lets this parameter be that treatment, that mean effect size that we want to study. So when we have a study that is aggregate data, this goes away, and we just have, and this is 1, and we have just the typical simple random effects model. Okay, so here this is what it looks like. So for an IPD study, our model looks like this. We standardized, so we've got residuals here that are now 0, 1, and normally distributed in a normal distribution of mean of 0, standard deviation of 1. And then for an aggregate study model, we have our typical. So this is this is sort of how it gets set up. And these are not the most interesting of the models. This is not the most interesting piece of why we would do this. But these are sort of how the models get set up, so that we have at the individual level some kind of where we can get a treatment effect that corresponds to the overall the study level treatment effect at level 2, basically. So the study data looks something like this. For an IPD study, we have our individual outcomes, our indicator that these are all from the IPD studies, what group each of the individuals are in, and a residual variance. And for the aggregated data studies, we just have one case. We have their outcome, their standardized mean difference. They're obviously from the aggregated data, so they have a 0 here. We give them a 1 for the group, and we have their residual variances are the variances for the effect size. So like as I said before, I think looking at the mean, sort of estimating the mean effect size is probably not the most interesting application of these kinds of models. The most interesting application is when we're thinking about moderators, okay? Because what our aggregated data studies can only contribute information at the level of the study. So we can only look at these moderator effects at the study level. But where it becomes interesting if we have the IPD data is to look at then within study information about how treatment effects might vary as a function of individual level characteristics, which is ultimately something we really want to get at. So IPD studies contribute both within study information about that interaction effect, really, with the moderator, and with information about between study effects. So when we want to add moderators to this model, then things get a little more complicated. We need a few more parameters because we have to recognize that we have an interaction of both within studies between any given moderator and the outcome, and then the between studies interaction between any given moderator and study level. So that's where these models end. Then there's lots of neat and clever modeling kinds of things to put in the models to parameterize it correctly so that we get at those issues. So for example, if we're interested in whether there are gender differences in treatment effect across studies, at the level of the study, we might only have % of female participants. And so we might do a meta-regression at that level looking at the relationship between % of female participants and the treatment effect at the study level. But at the level of the individual participant, we can actually look at what we could predict an individual's outcome by their gender, being in the treatment group or not, and an interaction effect between those two. So we get at that question of does the treatment effect differ depending on whether you're male or female, as opposed to how does the treatment effect differ given the percentage of females in the sample. Okay. So again, there are a number of ways to set up these parameters of the model, and we have a mix of IPD and aggregate data. And this gets at your question, Martina. For example, when we have studies that have a different balance of males and females. We need to parameterize the model to take that into account. We might have studies from IPD that only have males or only have females, and we need a bunch of different parameters for that. So there's a lot of sort of modeling tricks here that we need to put in when we don't have that kind of balance, or we have issues around the kinds of data we get from the IPD and the kinds of models we want to estimate at the study level. So Riley has, that Riley paper, where most of this is actually derived from, has all kinds of models like this to show how you might think about parameterizing both the level 1 and level 2 model to get at these issues of balance within studies, and also the between and the within study interactions with moderators. Okay, so they get a little complex. But let me show you why this might be important. So I have done one little one, and it's not a treatment effect. It's not a context of a treatment effect. It's a context of observational studies. So with my colleagues Ryan Williams and Josh Polanin, we looked at some data from a 2005 study that examined the correlation between socioeconomic status and academic achievement. Okay. So this was a fairly big meta-analysis. And then we included into that, into a selected number of those studies, a subset of studies, individual level data from 2 nationally representative data sets. The National Education Longitudinal Study, or NELS, and the National Longitudinal Study of Youth, NLSY. So the question in this particular meta-analysis was whether we know that there's a relationship between SES, socioeconomic status, and academic achievement in the US. Okay. And so one of the moderator questions that was asked in this particular meta-analysis was whether or not that the magnitude of that correlation differs depending on the percentage of minority students in the sample. Okay. So what we did was we took their data, and you can see here, these are all the correlations, and then the percent of minority in the sample. And then we also added, and there's more studies here in the paper, but we also added data from the NELS and the NLSY. 11,000 cases from NELS to 2,700 cases from NLSY. These are the correlations between academic achievement and SES and the percent of minority in the sample. Okay. So if we just take and do a standard random effects meta-regression model here, we get the following. And what I did was, in this case, if I just aggregate the data from NELS and NLSY up to the study level, get a correlation, do a regular standard meta-regression, I get a regression coefficient for the percent minority students in the sample of negative 0.146, but it's not statistically significant. 0 is in there. Okay. So basically, the random effects mean correlation is about 0.356 with that confidence interval. Okay. That's treating the individual level data as if it was just aggregating it up to the study level. Okay. But we are interested in whether or not that relationship between SES and achievement differs depending on whether you're ethnic minority or ethnic majority. So we're looking at, again, at an interaction between at the study level, we're looking at an interaction between % of minority students and the correlation. But the level of the individual student, just like we were showing a couple slides ago, we're looking at whether being ethnic minority somehow moderates that relationship between SES and achievement. So we're going to use an individual level model, which I don't show you here, but the individual level model for our IPD data is going to include an indicator variable for ethnic minority status, SES, and then an interaction effect for SES and minority status, in order to get at that interaction at the individual level as well as at the study level. So this is what we found. Let's look here. This beta 1 is the sort of the between study interaction between minority status and academic achievement. And so it actually is, in this case, negative and also different from 0. So at the study level, we're seeing that the correlation between academic achievement and SES is lower for studies that have higher percentage of minority students in the sample. Okay. Then at the individual level, this is sort of a representation of that interaction. So both of these parameters, these gamma 1 and 2, get at the interaction that happens within those two studies. Okay. So what we have here is an interaction between minority student status and SES, which is negative. So the higher minority student is coded as 1. Okay? So if you're a minority student and you have high SES, that correlation between SES and achievement is lower. So it's, in some ways, it's there, what we're getting out of this is that interaction between SES and minority status that we can't get sort of at the level of the study. Okay? So that while we might have guessed this at the study level in our results from the last slide, it's even, there's a nuance here that we couldn't have gotten if we didn't have the IPD data. So again, we've got what we get. I think the benefit of having that individual level data is that we get a little bit closer to that question of if we can imagine this was an intervention case, a little bit closer to that question of how do treatments vary as a function of individual level characteristics, as opposed to how do study level effects vary as a function of study level characteristics, which gets us close to what we want, but not where we really want to be. So we do get a little bit more of a nuanced understanding of what happens in these moderator effects when we have IPD data. Now there's lots of questions. This is one example. There's lots of questions I have about what this would look like. For example, we only have 2 studies here. What if we had more studies? This whole finding here is on the basis of only 2 studies. I'm not sure how far we want to generalize that, and so forth. We've got, I don't know what our power, we obviously had a little more power here because we're actually able to find an interaction effect, which we didn't find when we aggregated the data. So there's some issues of power here that I don't quite understand and would like to understand how much power we get when we have individual level data as well. Okay. In terms of computation, and maybe other people know more than I do, I used SAS proc mixed. We need something that can do random effects, a multi-level model, when you only have one case at level 1. Because for the studies, for the aggregated data, we only have one case at level 1. So we can do it in SAS proc mixed. Riley used it. Goldstein doesn't say, but I'm guessing he uses his own program in that particular case, MOWIN, and I can obviously give you the code. I spent a lot of time, as Emily can attest, to trying to get a good example for a treatment, an intervention case, and I just couldn't make it work. Couldn't make it work. So, so I think that, sort of in summary, there's a potential for the use of this, especially to look at those questions that we really care about, which is what works and for whom. Again, there's still lots of open questions about the use of this in the social and behavioral sciences. I need to understand power better. How many studies does it make it? How many studies do we need, sort of, to make this work? What should they look like? I think we're going to get into issues. In this case, I'm looking only at observational data. There may be some interpretive issues when we start adding, as we saw yesterday when Dimitri was talking too, about combining observational studies with other kinds of studies. But I think in general, I think there are some potentials that we can build on some of this work to really get at those questions that we care about. And also we need to also foster a much stronger collaborative research community. Maybe, I can't believe, maybe we need to be more like the economists who share their data in order to conduct some of these IPD examples. I keep thinking there's got to be cases. We've been trying to do this and thinking about how to do this, say, in context of reading interventions. In the U.S., there's millions, and there's so many studies, and small and big studies, on reading interventions, some of which are quasi-experiments, some of which are RCTs, that would be a really good area to think about doing IPD with. But we haven't quite gotten to the point where we've been able to obtain data on those. And I think we also need, as we always do when we're at the edge of these kinds of new techniques, we need better ways of doing it so that people who actually have access to the data can do this. So, okay. I know that there are packages for doing IPD, and in my looking at them, they didn't seem to combine both. They are packages for if you have only IPD. So we're not going to be in that situation. But anyway, here are some of the references, and yeah. So, and if you figure out how to do that, I'd be happy to know. So thank you.